Now we're going to go ahead and take a look at how to attempt this question in a couple of different ways. First off, I want to make sure that you really understand the concept behind whenever they talk about getting either no solution or infinitely many solutions, either of which is considered the special cases. When we go to the back of page 33, which is side 2 of our math reference document, notice how we have these 3 scenarios. The first of which is pretty common, just having one solution for when you have 2 lines intersecting. We call all 3 of these a system of linear equations. Now notice these 2 special cases. You could either have no solution if the lines are parallel, meaning they have the exact same slope. However, they have different y-intercepts, so they intersect the y-axis at different places. However, in this case, notice you still have the same slope. However, the y-intercept is also the same. That's why it looks like there's just one line, even though it's really 2 lines on top of each other, which means they have every single point in common, meaning there's infinitely many solutions. So how does this play out algebraically? In this particular case, we know that if they're saying no solution, graphically, that means the lines are parallel, which again means that the slopes would be the same, which they really already are. This one is in slope-intercept form, and this is already a slope of 2. So I don't want to change this slope, otherwise they won't be parallel. And the thing to know algebraically is regardless if it's no solution or infinitely many solutions, both the x's and the y's would eliminate. And then we'll look at that in more depth in just a moment. So the fact that the x coefficients are the same means I don't need to multiply either equation by any kind of constant to make it so that the x's and y's are the same. The x's are already the same, so that means the coefficients of the y's must also be the same. Well, the coefficient of y in this bottom equation is 1, since nothing's written, so we assume it's a 1. That means a must also be 1. That means the answer is 1, and you can move on. However, I want to show you how that plays out and why that's the case. So let's say a were 1. Let's go ahead and plug that in there. That means you just get 1y equals 2x plus 1. And then down here you have 1y equals 2x plus 2. At this point, if I were solving it algebraically, again, we finished the problem several seconds ago. Now we're just showing how it plays out and giving you an important lesson about what happens in these special cases algebraically. Now at this point, we really have 2 algebraic approaches. So let's go back to that same page, really side 2 of page 33, but we're gonna go a little bit lower. And we look at the difference between when to use substitution and when to use elimination. So substitution is really convenient when either a variable is already isolated, like this one down here, or if one of the variables has a coefficient of 1 or -1, meaning you could easily isolate it. Elimination, on the other hand, is convenient when they're either both in standard form and or none of the coefficients are 1 or -1, meaning if you tried to isolate one of those variables to do substitution, you'd get some fractions which are difficult to deal with. Now, in our case, it's interesting because both of these have y isolated. So that definitely is a substitution scenario. In fact, let me give you an analogy here. Let's say 4 plus 1 equals 5, which it does, and 2 plus 3 equals 5, which it also does. The fact that they're both equal to 5 means they are equal to each other, which they are. In the same way, since 2x plus 1 is equal to y and 2x plus 2 is equal to y, you can say that 2x plus 1 and 2x plus 2 are equal to each other. Now at this point, we have 1 equation and 1 unknown instead of the 2 equations and 2 unknowns of a system of linear equations. And so now we can solve for x. I always recommend moving the variables first and then the constants, because notice what happens is the x's totally eliminate, which we talked about. And then you're left with 1 equals 2, which is a false statement, meaning there's no solution. If instead it was the infinitely many solutions case, you would have had a true statement like 1 equals 1, 2 equals 2, or 0 equals 0. Now, another approach you could have taken, which I think the algebraic approach in this case was the easiest from the very beginning of just figuring out what it would take for the coefficients to be the same, which we didn't have to do anything. We just were able to look at it and see a is 1. But what you could do is use Desmos. And I just want you to be familiar with this approach. So let's go to the upper right corner, open up Desmos right here. And then sometimes you need to reorient things a little bit. If you press Control 0, it goes back to the normal viewing window, which can definitely be convenient. Or you can press Control plus to zoom in a little bit at least. I'll do that a couple times. And if you have a touchscreen, you can drag things around, which is nice. So let's go ahead to Desmos and type these in. Now, because a represents a constant, which it says down here in the directions, we can actually type that in. So we'll put ay, and it creates a slider for that constant, which we'll look at what that means in a moment. We'll press enter. It creates the slider for a. Now, for the second equation, I could put y equals, but with Desmos, that's the one time you don't have to type it in, is when it's y equals, so I won't. And let's go ahead and take a look at what we have here. We already know that for there to be no solution, the lines have to be exactly parallel, and they already are, which is why a equal to 1 is definitely the correct answer. However, if it weren't immediately, you'd be able to move the slider to see what it would take to get the lines parallel. Now, I think it's a great approach. I just think sometimes it's a little bit difficult, especially if the answer had been a decimal, which it doesn't seem like College Board does to us, which is nice. It would be really hard to be able to see when the lines are exactly parallel. However, this is another good approach to be aware of with this slider feature on Desmos. Regardless, we got our answer as 1.